All right, so the video recording has started. I hope I am audible to you all. If someone should unmute and tell me, otherwise I won't be able to do. Hello. Okay, I can hear my echo from the pad. So I expect everything is going fine. I'll just start the class. Okay, so welcome to week 8 discussion session. So this marks at least uh, two-third completion of the course. Even though on the course webpage, content till week 10 has been released, but I hope so far your course has been going smoothly and you have been able to sail through the assignments relatively easier because of the discussion sessions we are having so far. So any questions you have from the previous weeks, anything so far, you can always get back to me and ask. Uh, okay, so my plan today is I'll continue from where I left off and see how far I can go with 2 hours today. Maybe I won't take 2 hours today. I plan to complete it a bit earlier. Let's see. Let's see how the response goes, and then we'll continue with what till wherever we can go. All right. So just a second. Okay. So we'll start off from where we left, obviously. So last class we ended by defining eligibility traces. Actually, we haven't defined eligibility traces, but we were looking more at the forward view uh, cases. In fact, eligibility trace definition comes when we define for the backward view, right? So let me quickly highlight this. Okay, so to just give a quick summary, I'll just draw the diagram. I think it's easier to explain when I have a diagram with me. So let's say this is state ST. I'll just copy, paste, this goes here, paste, this goes here. Let's see. Sorry, this goes maybe here, this goes here, this goes somewhere here. I think this is fine. And let's say this is the terminal state, which are represented by the dashed box lines. And this is state st plus 1, this is state st plus 2, st plus 3, and dot 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 till you reach some terminal state. Okay, so this is how the state transition looks like. This black box corresponds to the action. For each action you take, you get a particular corresponding reward RT plus 1, RT plus 2, RT plus 3, and so on. Okay, so these all are the viewpoints that we know. Imagine a person or imagine an agent is sitting or standing on state ST plus 1. Now, the way the person wants to estimate or try to leverage the advantage of an n step return or a lambda step return is it starts it starts looking ahead to see how good each version of the state is, and based on that, it takes a lambda weighted average over all of this, right? So if you draw this, let's say red color, so the agent looks here, here, then here, and eventually tell this. So let's say the reward you get here is RT, right? Or here, this this back dot is RT. Yeah. This is RT. Fine. That's the agent looks over there, and this is the time axis, and this whole picture is called as the forward view. Okay. So this is a diagram I have picked directly from the Sutton and Bartow second edition book. I think this more or less gives an idea of what the forward view mechanism looks like. And in fact, if I were to write down the return, the lambda return for the forward view, it looks like this. So I have gt lambda is equal to 1 minus lambda gamma, and from 1 till t minus t, this is lambda n minus 1 g of t n plus lambda, the remaining time. I just do the direct Monte Carlo return. Okay. So what this update rule tells me is that for each time step up till time horizon t, I can do infinite step backup. So essentially, this is what this is doing. So instead of doing infinite step backup, I do the backup till time step t minus my current time step t. And all the one step, two step backup I do, I weight appropriately with a lambda weightage. So the one step return gets a weightage of lambda, the two step return gets a weightage of lambda square, lambda cube, and so on. Okay. And the way this heuristic is taken is sort of arbitrary. If we are considering only the forward view case here, and this usually makes sense when we look at the backward view, and this notation has also been taken in the forward view case so as to make both these viewpoints equivalent in a way. Okay, so till that point you take the lambda step return, and after that, beyond time step t minus 1, or beyond time step t minus t, you take the full Monte Carlo return. Okay, this was something which was discussed till the last class, so maybe I should just highlight this. This is an important update rule for the forward view case. Okay, so this way we understood, or we have come to appreciate how well a lambda step return can be used to leverage the lambda step return, right? How well having a combination of multiple of n step returns of different sizes of different values of n's could help us leverage the advantages of sampling along with bootstrapping. Okay, so in a way we are extending what we had for td0 case, and we are going towards td lambda case. So this is the whole viewpoint for the forward view. Now just copy paste this. The changes are minimal. Okay, so the same thing here. Let's see. Okay. Now, finally, as we start with the backward view, we can formally define what we mean by an eligibility trace, and why forward view, while it looks cleaner in mathematics, is sort of inadequate. Okay, I'll just go back to the previous slide. So you see the way the forward view has been formulated. It's very easy to understand. Mathematically, the formulation is very neat, but there's one big fundamental problem. And that problem is it violates the laws of causality. It means being at state st plus 1, I need to have an infinite horizon up till time t, up till the end of the episode. And only then I can make my update and so on. Okay. But from an implementation perspective, or from a mechanistic perspective, this sort of becomes difficult for us, or for when we are doing any sort of implementation. This kind of keeping track of all the future states becomes very difficult. Okay, so to make it easier to implement and to easier to work with, so we the view of backward traces was introduced. So the way backward traces works is as follows. Let's say I have a my x-axis represents the times of visit to state S. Okay. So I have a state S, and this represents the time of visit that I have made for each state. Okay. So this axis represents the time, and this axis maybe represents the number of visits I have made to that state so far. Okay. So this is how the eligibility traces looks like. So for each time step I visit, I get a value of 1, and that starts decaying exponentially. And again, the next time step I visit, I uh, uh, add a +1 to it, and so on. So implementation wise, sorry, diagrammatically, this should look like this. For the first occurrence, I get a value of 1, then it starts decreasing slowly. Immediately I saw it again, I increase, again I increase, and so on. Okay, and then it goes to decrease, and then moment I see something, I update, and then here one more update, and so on. Okay, so now this represents the time of, so the number of times I have visited each state in here. So this is 2, and this is 1. Okay, so this tells me the times of visit to state S, and this is some sort of stimuli that is being experienced by making a visit to that particular state. Okay, so now we are in a position to define a new quantity known as eligibility. Okay, so the way this is defined is we define et of s is equal to et of s is equal to gamma lambda e of, sorry, just this gamma lambda e to the e of t minus 1 s if st is not equal to the current state. Otherwise, st plus 1 if s of t is equal to s. So what this equation is saying is something similar to what I have represented in the above diagram. So the eligibility is a quantity associated with each state. So each state has a parameter called eligibility. Initially, the eligibility is 0. The moment I encountered a particular state S, the moment I encountered that particular state S at time t, my eligibility becomes 1. Okay. And for the next time step, I don't visit it. The eligibility keeps decreasing by a factor of gamma times lambda. Okay. So there are two factors in play. One is gamma, one is lambda. And based on that, it keeps on decaying exponentially until it again encounters status, and then it gets a value of +1, and so on. Okay. So you notice there are two factors over here that are playing a role. One is the gamma, one is the lambda. So what is gamma here? Gamma here is nothing but the discount factor that we have. So the discount factor is basically uh, what? It's telling me how spatially close my outcome was relative to like how spatially close the outcome was relative to the previous time step I had visited that. Okay, so this is basically a parameter of the problem itself, because changing the value of gamma changes the policy that I am trying to learn. Okay, and here lambda represents the lambda step return that we had seen in the forward view case. That the for looked at the forward view. So lambda return is basically lambda weighted average over the one step, two step till the n step return, till the infinite step return ideally. Okay. And lambda here is basically a parameter of the solution itself, because changing the value of lambda doesn't necessarily change the policy that I have. It changes the way learning happens, but the policy or the optimal policy still remains the same in this case. Okay. So both have this slight difference over here. Just a sec. Yeah. So let's say I have defined eligibility. Okay. So this quantity is called the TD error, right? This uh, delta T is fixed to is a fixed notation to define TD error. So when I say TD error, what it means is that means I took a one step return, which is I basically sampled for one step action and then I bootstrapped that particular return. So I have RT plus one plus gamma times V of ST plus one should be V. Okay, this is V of. Let me write it in VT. This is gamma V of ST plus one minus V of ST. Okay, so this is the TD error that I have. This is the term that I get when I write the update rule for TD and the bracket term that I have. Okay. Now, when I try to do an online updation of sorts, so I can say that my change in the value function, which is VT of S, delta VT of S, which is the change in the value function that I have, is equal to lambda, sorry, alpha DT ET of S. And eventually my V update looks like this. So VT of ST plus 1 is equal to VT of ST plus alpha times delta T ET of S. Okay. So here in the TD updation rule, this is the same as the TD updation rule. Only I have added this has the update part or the TD error part has been multiplied with the eligibility part. So in a way, you can think of it like this. So let's say you have visited some state previously back. Let's say you have visited some state and you have moved forward in time. Okay. So a way to look at it is that you have put some sort of marker on that state, which kind starts decaying over time. So let's say I have some particular state that I have visited beforehand. So the moment I visit one particular state, I put some big red marker over there, and with time the marker sizes decreases. So let's say the this quantity represent the area represents the size of the marker. So the most recent visited state will have a bigger marker over here. Okay, so in a way, if you have seen how ants move in a straight line, okay, so the way if you have seen how an ant colony moves, so when they move in a straight line, they release some sort of a pheromone. That's kind of a disappearing trail that they release when they move in a straight line, and this in a way allows the other ants to follow in a straight line so that they reach the respective goal. So this is the basic idea behind an eligibility marker. So marker is not a technical word that I am using. This is just to make you understand what uh, I mean when I say eligibility of a particular state. It means how eligible a particular state is at time t to be updated, which had been encountered at some earlier time t prime, okay, or t minus 1. Okay, so this gives me a method to update the value function in an online fashion, right? So this, sorry, so this type of method, so this is a kind of online updation that is happening over here, right? And again, I should highlight this particular update rule, okay? And maybe we number it equation 2, and the previous one we number it equation 1. So that's when we refer back, sorry, so when we refer back, it's easier to recollect, right? Now, This particular trace that I have mentioned, this has a name to it. Okay, so this kind of trace is known as accumulating trace. Meaning that each time I encountered that particular state, so whatever current value of eligibility that I have, I add a one to it. This is also what this equation 3 is also telling me, right? So each time I encountered state S, along with the current eligibility, I add a value of 1 or any other number. It need not be 1. Any number is added to it. And this is how the eligibility is computed at time t plus 1, right? So this is one sort of a trace that we have. Another type uh, is known as replacing traces. Okay, so again, this is times of visit, times of this is times of state visit, and this is the eligibility trace. Okay, similar way this works is the moment I encountered a stimuli, this gets a value of 1. Okay, let's say this is 1, this is 0, and this was 1. Okay, so we don't want the eligibility to sort of grow unbounded, right? So we don't want, so in the accumulating trace, the upper bound of the eligibility is not defined. Okay, if a particular state keeps on getting accounted for like often enough in a particular episode, then the eligibility for that state keeps on rising exponentially, right? So in order to avoid that, there is another way that another kind of trace that is known as replacing traces. So initially, if for the first visit to a state, you get a value of 1, then it starts decaying. The next time you visit that particular state, instead of that 1 being added to the current eligibility, you replace that. So you say that the eligibility becomes 1 again, and then it starts decaying again, and then it becomes 1. Okay, till it reaches here. Again, it becomes 1 if I visit it. Let's say two occurrences occur here, and here, let's say single occurrence. Fine. So this is the number of times state has been visited. Okay, so this kind of traces is known as replacing traces. Okay, so I'm replacing the trace that I had encountered so far with the value of 1 for every new visit that I make to that particular state again. Okay, so if I were to represent it mathematically, this looks like et of s is equal to, this is gamma lambda e of t minus 1 s if st is not equal to s, else it is 1 if st is equal to s. Okay, so this is another type of trace. Now, just a broad look here. If I were to look at it from a Monte Carlo kind of a view, so we go back to the eligibility part over here. So you just take a look at this online updation rule, which is equation 2. Okay, so now when I compute the eligibility, so I have a gamma lambda term, right? So the moment I set lambda to be equal to 1, okay, so the moment I set lambda equal to 1, what I get is I get my TD 0 when I put lambda 1. Basically, my TD lambda when I put lambda equal to 1 becomes TD1. So TD1 is essentially the Monte Carlo method, right? So if I, let's say, put lambda equal to 1 in equation 1 over here, so this entire first term vanishes. It becomes 0. only the second term remains, and that also becomes gt. So my gt lambda is essentially g of t, right? Which means I am looking at the Monte Carlo method. So the important point here is what equation 2 tells me. When I put lambda equal to 1, it gives me an incremental update for the MC version or for the Monte Carlo version. So what it essentially tells me is that if I am trying to do Monte Carlo, the only way I can update the value function is when I reach the end of the episode, because only after I reach the end of the episode, I get the value of GT, right? And after I get the value of GT, I trace back and I update the value function for that particular state. So this updation also gives me an incremental method or an incrementation updation for MC version. Okay. So this is another power that the idea of eligibility traces proposes. So by introducing this the uh, terminology of eligibility trace, we can do the same incremental updation, but for a Monte Carlo method kind of a thing. Okay. Similarly, there is a third kind of trace which lies in between. Before that, so now that I've introduced about the incremental update for Monte Carlo version, so you see, just by looking at the accumulating trace and the replacing trace, you would see that this accumulating trace falls under the category of every visit Monte Carlo, right? If I set lambda equal to 1, this essentially falls under the category of every visit Monte Carlo, whereas my replacing trace falls under the category of, where should I write? Falls under first visit. No, too small. First visit Monte Carlo. Okay. Now, another version of it is known as Dutch trace, which sort of lies between my accumulating trace and replacing trace. And instead, it gives me a parameter to control the amount of accumulation I want or the amount of replacement I want. So that kind of gives a weighted combination of both these two approaches. So for Dutch traces, the eligibility trace update looks like this. So my ET of S uh, is equal to gamma lambda ET of minus 1 of S if ST is not equal to S, or otherwise I have beta gamma lambda ET minus 1 plus 1 if ST is equal to S. Okay. So here I've introduced another parameter called beta. So this beta gives me a way in which I can sort of control the amount of accumulation or the amount of replacement that I want to do. So in this case, if beta is equal to 1, uh, yeah. So if beta is equal to 1, it means it's same as the accumulating traces. And if beta is equal to 0, then this is equivalent to the replacing trace. Okay. So beta gives me a middle ground wherein I can control uh, the weightage of both these two approaches. Okay. Now, like I had said earlier, uh, when I'm looking at eligibility traces, I have two parameters through which my eligibility decays. Okay. First is the gamma parameter. Second is the lambda parameter. So this gamma parameter is also called as the discount factor. Okay. And this is a parameter of the problem itself, right? That means for changing the value of gamma, my policy changes. So if you can recollect, we had discussed the heaven hell example, wherein if my gamma is higher, the agent goes to heaven. If the gamma is lower, then you would end up going to hell. That if you recollect that particular example. And lambda is the parameter for the lambda step return, right? The return parameter. And this is, sorry, this is a parameter of the solution, meaning any value of lambda that I take, uh, I will eventually converge to optimal solution. Okay, eventually all values of lambda will converge to the optimal solution. Only what it matters is the rate of convergence. Okay, so that eventuality is there, but how quicker or how slower my convergence occurs, that is dependent on the tuning of the lambda parameter that we have. Okay, this is something to keep in mind. Lastly, to just summarize the backward view, I'll just draw a similar neat diagram. So I have state ST, which I'll just copy paste here, 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 and so on. Okay, so let's say my time is moving in the downward direction, and my agent here, sorry, my agent is sitting at state S. Okay, and is sort of looking behind. Okay, so the agent need not explicitly compute the values of the previous time set because it has, right. So let's say this is state st plus 1, this is state st, this is st minus 1, st minus 2, and let's say this was the reward I got, which is r of t minus 1. To reach here I got a reward of, sorry, this is rt minus 2. To reach here I got a reward of rt minus 1. Here I reach, to reach I got rt. To go here I got a reward of rt plus 1. Okay, so the agent actually takes a look at the eligibility of each state that I have. Okay, so the eligibility is also a metric that we are keeping account of when we are looking at each state behind. So let's say each state has an eligibility. So this is eligibility. Okay, let's say this is ET of the state, ET of this particular state, ET of the state. Okay, so based on the eligibility that I have, whenever I try to make any sort of updation here, I just take a look back and look at the eligibility. Based on the eligibility, I make an update. I go further back, see the power of the eligibility that there is, or the high value of eligibility signifies a higher updation, right? So this is essentially what the backward view tells me. Okay, so both these viewpoints are equivalent, the forward viewpoint and the backward viewpoint. You can always establish the equivalence between these two classes. Only issue is that when we have a forward view, we have a neat way of visualizing this problem and introduce eligibility traces. Like eligibility traces comes with the backward view, but forward view has a neat method of showing how the updation, how we can actually move from TD0 to TD lambda. But implementation wise, it's very difficult because of the issues with causality and such. So that's why we had to people had to come up with the notation of the backward view so that each state has some eligibility, and looking at the eligibility, looking at the strength of the eligibility, that particular state is updated accordingly, right? So that's the whole idea behind this, behind eligibility traces. Okay, Now, now that we have completed eligibility traces, the obvious thing or the obvious continuation for this is the eligibility traces control. Okay, so now that we have defined eligibility traces, it only makes sense to look at the control aspect of eligibility traces, right? So far we saw that my TT lambda is basically an estimation method. Okay, based on TD lambda, I can't recover the optimal policy pi, right? So in order to do that, I need to look at some sort of control methods in which I can recover the optimal policy pi, right? These are two control methods. Now again, when I want to look at control methods, so the eligibility traces earlier was defined for a particular state S. Okay. The moment I say I want to look at the control aspect for eligibility traces, then I no longer have an eligibility trace for a particular state S. In fact, the modification here looks like this. So the eligibility traces or the eligibility value is maintained for every state action pair that occurs. Okay. And the update rule stays similar. So I have, okay, this is true if ST is equal to S and AT is equal to A. If that particular state action pair is encountered, then I add a +1 to the decaying eligibility. Otherwise, only the decay happens. Right? So this is an idea for eligibility test. Now, okay, this if you look at it, this is a method for accumulating traces, right? So this is how accumulating traces works. In a way, you can also use the replacing trace also. Okay, so if replacing trace, if you want to use, so you remove this term over here, only one is put in that. So you remove this first term here, only one is put there, everything else vanishes. Okay, so this is how you can do. But turns out there are some problems or some MDPs where accumulating traces doesn't work as well as, or maybe we need to look at replacing traces. Okay, so the example goes like this. So let's say I have one state and I have a terminal state. Okay, I have two states, and from this state I can take two actions. So I can take action A1 for which I get a reward of 0, else I can take action A1 for which I get a reward of +1. Sorry, action A2, action A2. So in this sort of MDP, the trajectory looks as follows. So I keep on taking action A1 repeatedly, meaning I keep reaching the same state until I take action A2. The moment I take action A2, my episode is over. Okay, I reach the terminal state. So the trajectory somewhat looks like this in this case. So I have, maybe it could be A1, A2. So in the sorry. So it could be, maybe the first action I take is A2. Otherwise, I can take A1 some three times. Then I take A2. Otherwise, I can take A1 some very large number of times until eventually I take A2. Okay. So this is how the sequence of action looks like. So now, when I'm looking at the eligibility trace for each state action pair, so if action A1, if action A1 has been taken k times, okay, if that particular action has been taken k times, So the way the eligibility for action A1 could be updated is as follows. So action A1 would have roughly this many number of updates for the eligibility uh, for action A1, whereas action A2 eligibility would be updated only once. Okay, so now this causes an issue because obviously we know that action 2 is a better action as compared to action 1, but since action A1 has very higher number of occurrence in comparison to action A2, so naturally the eligibility for action A1 is significantly higher than the eligibility for action A2. So the moment we make use of an accumulating trace, so this causes an issue in this case. Okay, because I don't want the accumulation to be so large so that it kind of offsets the update that I make to action A2. Okay, so in order to you know kind of remove that particular problem, so we make a use of replacing traces in that particular case. So there is one aggressive version of replacing trace, and the update is as follows. So I have FST. So it's one if ST is equal to S and AT is equal to A. It's zero if that action was not encountered, but that state was achieved, if action A was not reached, or it is this quantity otherwise. Okay, so what it tells me is that the moment I encountered a particular state action pair, I set the eligibility to be 1. For all other states that don't have action A, okay, no. So for all other actions which are not equal to A, the eligibilities are set to 0. There is no decay. If a particular state is visited, the target action, if it is achieved, I get a value of 1. If the target action is not, I mean, for all other action which is not the target action, this will get a value of 0. It is replaced by a value of 0. Otherwise, for every other state which are not visited, I have the normal lambda gamma decay over here. Okay, so this is the basic idea. Now, if I want to look at the control aspect for eligibility traces, okay. So for TD methods, there are two popular control algorithms. One was the SARSA, and the other is Q-learning. Both which we had seen in the last lecture. We had also done 2-3 tutorial example code to understand what is the difference between the update rule for SARSA and Q-learning. SARSA is an on-policy method wherein the action sampling that is done in policy, and the next action that is selected is not bound by a policy pi, rather it's an exploratory action. Whereas in Q learning, the policy updates are, or it's an off policy method, okay, and the action that I select is necessarily the max possible action that we take. Okay, so to start with SARSA lambda, method is fairly straightforward. Okay, instead of v function, we start with the q function. So this eligibility trace has been defined, and the forward view looks similar. Okay, so or the forward or the backward view for SASA lambda is more or less straightforward. Okay, so I compute the q value. I put an eligibility marker times for each number of time each state S was visited, and then the q update. So first I define the delta q. So I have delta qts comma a. is my alpha dt et, right? So only difference is that the eligibility that I'm computing is not for a particular state S, but for a state action pair S comma A, right? And here dt is the TD error for QLearn, sorry, for SARSA. My bad, my bad. So dt is the TD error for SARSA, which is gamma QT ST plus 1 comma AT plus 1. So this action AT plus was in a, AT plus 1 is an exploratory action minus QT ST AT. This is as per the SARSA update rule. Okay, so this DT, this is how DT is computed. And eventually my QT of ST plus 1, so my QT of ST plus 1 comma A T plus 1 is equal to QT ST AT plus this delta T US TAT. Okay, so just making a note of the important thing here. This is how the SARSA lambda update looks like, and this is how my DT for SARSA lambda looks like. Okay, so if I were to draw it, how SARSA lambda looks like, the backup diagram. Okay, so this is the backup diagram for SARSA lambda. So let's say, so here I don't start with status, okay, because I'm dealing with a state action pair. So I start with state action S1. I move one step forward. Okay, make an update. Okay, similarly, so I go here and then I increase it further. It's a two-step update. Here, three-step update, so on until we reach the end step update rule. Let's see. This is how the end step updates should look like. Okay, so this is one step, this two step, this three step, this end step, and eventually I make it go further ahead. You see. Okay, let's say this goes further ahead till I reach some terminal state. So this is similar to my MC. Okay, so this is the backup diagram for SARSA lambda. Cool. Now, now we have defined for SARSA lambda. We uh, will look at something called Watkins Q lambda. So again, this is a control method for Q lambda, wherein what I'll do is uh, I'm extending the idea of Q learning to Q lambda, and there are different variations on which people have defined the control for Q lambda learning. But this Watkins is the most popular algorithm. However, implementation wise, this doesn't work as good uh, as it looks in theory. Okay, so for Q learning, this is how the error term looks. Okay, this is how the update for Q learning looks like. So I'll just color this. Okay, and here for Q learning, uh, it's kind of tricky. Okay, to define the control for Q learning because every time the next action that we are selecting is selected when by taking the max of that particular action, right? So let's say I am in state S. So I take action A. I go to state S prime. Action A is fixed as per the Q value because first action I take, I have no choice with regard to that, which is given to me. Okay. I reach state S prime. After that, I always behave optimally. So to reach state S double prime, I take the max of A prime. Okay, I'll take the max action basically. And later to reach S triple prime, sorry, to reach state S triple prime, I take max of the second action. Okay, so in a way, what uh, what Watkins Q lambda tells me is that I'll just write it down. It tells me you keep accumulating ET. ET stands for eligibility traces for greedy actions. Okay, so as long as I'm taking a greedy action, according to my Q learning, as long as whenever I'm doing updating the Q value for Q learning, as long as I'm taking the greedy action, I keep updating my eligibility traces for greedy actions. But for the first time, explore, I take any sorry, for the first exploratory action that I have, for first, sorry, for first exploratory action, you do normal Q learning update. Okay. So this is what Watkins Q lambda algorithm tells me. For every greedy action that I take, for every greedy action that I keep encountering, as is the case with Q learning, because I am only concerned with the max of the A prime. So as long as I'm taking a greedy action, I keep a track of the eligibility traces. I keep accumulating that and make updates with regard to the eligibility traces. But the first instance, the moment I encounter an exploratory state, or sorry, the moment I encountered my first exploratory action, I stop accumulating my eligibility traces and do my normal Q learning update, right? So the ET update looks like this. So this is gamma lambda E of t minus 1 s plus 1. This is the accumulating trace. If st is s, at is a, and at is also the argmax of the particular action, right? So if at is argmax of q st prime a. Okay, so I keep accumulating that particular trace. Otherwise, if not, so this is true for all other actions. Okay, so the if I keep on taking a greedy action, if that particular action is greedy and that is the target action in this case, I do the update in the first line. Otherwise, for all other actions which is not equal to a, so for all at not equal to a, and still at is the greedy action. Okay, so for the greedy action, I just add a +1. For all other actions, non-greedy actions, I uh, just do the decay of the eligibility trace. Okay, so this is what this line also mentions. So just keep this in mind and see the math that I'm doing. Otherwise, the moment I take a first exploratory action, then I stop accumulating all the eligibility traces and I do my normal Q learning update. ET vanishes, right? So this is true if it is not equal to argmax of a prime q st prime comma a. Okay, and the backup diagram for Watkins q lambda looks as follows. So just copy paste this. This is the one step return, and it is this. This is the two-step return. Okay. Now understand that all actions that I'm taking is the greedy action. So this is max of a. Okay. Again, all of this is with respect to max of a, right? And then copy, paste, I extend it to a three-step update. I have three-step, then I copy, paste. Let's say I paste it somewhere here. And this is an extension till the n step update rule. Yeah. Okay, so this is the update till the n step rule, or let's say this is till I reach the terminal state. Okay, so let's say this is the terminal state. If I reach the terminal state, I keep on as long as I'm taking the greedy action, I should be fine. Okay, as long as I keep on sampling the greedy action, I should be fine. Or let's say I sampled multiple number of times, but then I reach a particular state wherein I no longer do the max of action, but instead take an exploratory action. Okay, so in this state, I do some kind of exploration. So in Q learning, the moment I take an action, which is not the exploitation action, which is not the greedy action, but an exploratory action, I stop the update and we start again. Okay, the eligibility becomes zero basically. Fine. Okay, so far so good. So I think this was all that we were supposed to cover in the last class. This was missed last class. So uh, maybe we can go ahead with the content of week 8, which is function approximation. Okay. By the way, please feel free to ask any questions if you have any doubts remaining with what we have covered so far. Okay. So till week 7, all the kind of methods that we have looked at were essentially value function based methods. That is, we compute some estimate of the value function, and based on that, we recover or extract the optimal policy. Okay. Two methods were there. One was the policy search and the reinforce algorithm that didn't work with the value space, but rather with the policy space. So that's a policy gradient kind of a method. But apart from those two, all the different kind of methods that we have looked at were value function based approaches. These are the value function based methods, right? So essentially, what uh, happens is, just a sec. So what happens is you have some sort of a lookup table. Okay. So what happens in value function method is, let's say you have a bunch of states. Okay. So you have a table. So you have a bunch of states S, and you have the corresponding value functions V of S. Okay. So you store S1, you update value of S1, and so on. Okay. So it's a tabular representation. Similarly, for Q function, you have for each state action pair, you have a corresponding Q function. So for any state that I encounter, I just make a query to this table, to this lookup table, and figure out what the value function that I've estimated so far is. And based on that, I take my next action or I do my update and other methods. Okay. It turns out such kind of methods. Yes. Okay. It turns out such kind of methods have some obvious drawbacks. Okay. The first kind of drawback is let's say I have 10 states. Okay. Then it makes sense for me to go for a value function based method, right? If I have 10 such states, I know I'll visit each state often enough. If let's say my episode length is 10,000, so each state I'll roughly visit around 100,000 times, and I take the average of all the rewards that I've received so far, and I update my value function. Okay, imagine number of states is 1 million, or even better, it's around 10 to the power 10 or 10 to the power 20. Okay, because whenever we are solving any kind of real life problem, the number of states is humongous. Okay, so let's say I have a billion state space. Okay, and if I want to use a value function based method for that, I not only need to visit each state once, I need to visit each state often enough to have some good estimate of the value function, right? If I don't visit it a few number of times, then the estimate for the value function that I've made so far would be sort of inadequate, right? So this kind of method sort of requires me to visit each state often enough. So this is memory intensive. So that's one obvious drawback. Secondly, this value function based methods has no method for handling continuous states. Okay, this also is missing. Thirdly, there is a lack of generalization. There is a lack of generalization, meaning for every state that I encounter for the first time, and I in testing, okay, not in the training part. Let's say for every new state that I encounter for the first time, I won't be able to generalize because I don't have that particular value fed into the representation or the lookup table, so I can't look at it. So the generalization becomes an issue, right? So the solution to this is if we can have some sort of a function instead of a value value table based method, let's say we have some sort of a function or some sort of a parameterized representation, some sort of a parameterized representation, then we don't need to have any such table that we need to look at. Rather, we can estimate for any state S, our parameterized representation should be able to estimate the value function for any unseen states. Okay. So the more number of parameters that I have, the better is the estimation or the prediction of the value function that I can make for that particular state S. Okay. And obviously, the moment I do that, there will be biasness with respect to parameterization, with respect to parameterization. So the way I parameterize the value function is important here, because if not, the representation would have an inherent bias in that, and no matter what you do, it will never be perfect. Okay, so if my number of parameters that I have is in essence equal to the number of states that I have, then in a way that I am saying that it is similar to what I have done in the lookup table kind of a representation. Okay, if my number of parameters, let's say my number of parameters theta, if my theta is almost equal to state s, closely equal to state s, so that is essentially my lookup table representation that I'm looking at. Reason being that for each particular state, I have some value function that is a particular parameterized representation for that. Okay, so the idea is, in order to remove all these drawbacks, I want to have a very compact sort of parameterization that in a way captures the essence of the function that I'm trying to uh, estimate or mimic, right? So this kind of method is known as function approximation. Let's see how far I can go today. Okay, cool. So this method is known as function approximation. Okay, so in function approximation, what we are trying to approximate? We are trying to approximate the value function, right? So I am trying to approximate the value function by some estimate, which is parameterized by parameters theta. Okay, so my v pi is approximated by some estimate of the value function, which is parameterized by theta. Okay, this parameterized by theta. And here, in order to measure the goodness of the estimate that I'm making, the goodness of the function estimate that I've made so far, I need to know two quantities. First is the choice of parameters that I have, and so the biasness can be reduced by the choice of parameters that I make. Okay, so the better choice that I make with respect to a parameters, so this could be heuristic or it could be intuition based or any ad hoc parameterized representation. Better yet, if in recent times, if you people are familiar with the use of artificial neural networks, so then you need not even bother with the parameterized choice. Essentially, the deep learning network kind of learns the parameters for us. Okay, so that is there. And second is a measure of error. Okay, so an error measure that I want, meaning how close my estimate is with respect to the true value function v pi, right? So uh, this error measure historically is represented by j theta, which is the cost function, right? J theta is the cost function, or the error measure is basically sum over all states, the difference between the v pi of s minus v hat of s comma theta, the whole squared. Okay, so this is known as the mean squared error, right? So this is if you guys have studied about machine learning, so you must be familiar with this kind of loss function. This is known as a mean squared error loss function, and this is how it's represented. This term is actually multiplied with 1 by n. That is, I take the summation over all the errors and then I average it over 1 by n. When I say 1 by n, what I mean, what my intention is that each difference in the error that I get, I'll give equal weightage to each of these terms. Okay. Rather, I can generalize it more and define d pi of s. So this d pi of s gives the kind of weightage that each particular mean squared error term needs to be given when I'm trying to measure the error. Okay. So here, this new term d pi of s is called the steady state distribution. Okay. Meaning, meaning when I fix a policy pi, the trajectory that I have, essentially my Markov decision process reduces to a Markov chain because there is no decision making that is being done over here. Okay, so for a choice of pi from a state S, I go to the next state and so on. So this d pi of S in a way measures the distribution of state or the occurrence or the frequency at which that state occurs when I'm following policy pi. That's why it's called a steady state distribution. And the way dpi is estimated is only by following that policy pi. I won't be able to estimate dpi of s if I'm following some other behavioral policy or some other estimation policy. So the only possible way, so possible to estimate dpi only by on policy methods. So I have to remain in the policy in order to estimate this dpi value, right? So this is something important one needs to keep in mind. So let's assume this dpi is there. Just to give it a more generalized notion, let's say we go back to the original 1 by n notation, right? Let's say each state is equally likely to occur and occurs with equal probability. So let's say that's why I average it with 1 by n. And also it's easier to compute that, right? So we'll eventually go back to dpi of s. So let's say start with this. Okay, so the way the updation happens is, so I have v pi of s st minus v hat of st comma theta the whole square. Okay, so this is the loss or the error measure that we have. So now if I have this, in essence I should be able to compute the error measure and find out a good enough value function parameterization that would help me approximate this particular thing, right? Just a second. Sorry, just a moment. Okay, but one big issue that people face or everyone faces here, let's say I colored this as well, I forgot to do this. So all this method is fine, but the biggest issue is that we don't have vpi, right? I mean, if I have vpi, then why do I need to estimate v hat of pi? The only reason we do that is so that we don't need a value function based method. We are trying to move away from that so that our approach is more generalized in nature, right? So this v pi of st, we don't have the exact value, so we need to do some sort of estimation here, right? So this v pi can be estimated by gt if you are following Monte Carlo, right? So gt is a good enough estimate for v pi. Otherwise, we estimate it by rt plus 1 gamma v hat st comma theta. This is if we are following a TD approach, right? So instead of v pi, we replace the actual value of v pi by an estimate, or should I say, yeah, a truncated representation. What's a good term? Estimate is not a good term. It is a sample value, you can say, a sample method. You can think of it as a sample for VPy that we have. And based on that, whether it is GT or uh, which is the Monte Carlo return or the TD return, based on that, that can be updated. In fact, the sample is the way in which we had in the initial classes defined stochastic approximation, right? Whenever we want to do any sort of incremental update. So you think of it like that way. So the moment we have that, we can optimize this loss function, and we can do it by using any uh, regression method that we know of, right? So let's say if you want to do classical regression problem, right? So what we need? We need some sort of a data set, right? So that data set is you have some x, you have some f of x, okay? You have bunch of different data, and from this, what my regressor learns is an estimate of f hat of x, okay, based on some data set which is available to us. Whereas in RL, such kind of data is not available to us. The data that we get in RL is essentially trajectories that we have. So when I say trajectory, I mean ST, AT, RT plus 1, then ST plus 1, AT plus 1, RT plus 2, and so on, right? So we have a big trajectory that we have. And from that, we need to extract certain information so as to uh, formulate it into a regression problem, right? So use the return, which is RT plus 1 plus gamma RT plus 2 plus dot. Similarly, I have ST plus 1, wherein I use RT plus 2 plus gamma RT plus 3 plus dot, and so on, right? This is one way to represent the states. Another way is you have state ST, and then comma you have RT plus 1 plus gamma V hat of ST theta, okay? Then you have state ST plus 1 comma RT plus 2 plus gamma V hat ST plus 1 theta, right? So this way, one can represent the data over here and plug in into this Monte Carlo update. This also should be highlighted. Okay, you plug this into the equation, optimize it. According to the loss function, you come up with the best possible V function method that you have. Okay, so one issue with such one issue with such methods is that uh, whenever I'm taking a data wherein the value function is approximated by a TD return, the issue is that sorry, the issue is that my target over here. So this function over here, this is the target. This part is the target here. Let's say different color. This is the target here. So the target in here is also represented by. Hmm, I mean, the target is also estimated by V hat of ST. So the left hand side of this square term, not the so inside this square bracket over here, the left hand term is also dependent on V pi. The right hand term is also dependent on V pi. So if you look at the rule based method wherein we do target minus current estimate, we see that the target is in a way non-stationary because any update that I make to my current estimate, that in a way affects the target, and that means that the uh, any error or any biasness that is introduced in the current estimate that I have, that will again affect the target. And that means in essence, I am always chasing a moving target. Okay, the target is non-stationary. It's like I'm shooting a target, which is shooting or trying to reach closer to a target that is also moving in itself. Okay, so this kind of method introduces a lot of variance whenever we are training this kind of data. So one way to fix this moving stationarity thing is that we say whenever we update the value functions over here, we don't update it for the target. So we keep the target fixed for certain time steps. We update the uh, value functions for the current estimate, and the target is also updated, but the frequency of target update is much lower than the frequency of update of the current estimate. Okay, in fact, this is uh, an idea which is uh, used in many popular reinforcement learning deep RL algorithms in today's time, be it DQN or TD3 or SAC, such kind or any non-actor critic based methods. So this kind of method is always used. So the target update happens much lesser times as compared to the current estimate that is happening. Okay. So the moment this data representation is done, what we can do is uh, so the moment we have the data set with us, so the optimization can be done by means of gradient descent, right? So in classical machine learning, we know the concept of gradient descent. In fact, better yet, the concept of stochastic gradient descent tells me that any update that I make, I can do it in a pointwise manner. So that's the power of SGD, of stochastic gradient descent. Okay, so similar updation rule I update here. So this is how my theta update should look like. So I have theta t plus 1 is theta t plus my gradient with respect to theta t, and what goes inside is the mean squared term, right? So which is r of t plus 1 plus gamma v hat st plus 1 comma theta t. I should mention the subscript t minus v hat st theta t, the whole square, right? This is how the update rule should look like. This is also highlighted here. Cool. So now, once this is done, now the next part is how well we encode the state that we have. So the state for a particular MDP uh, has multiple different types of representations, right? So let's say my state S can be parameterized by some phi representation, right? So when I say state, my state can be broken down into multiple phis. So I have phi1 of S, phi2 of S, dot, phi k of S. So this state representation or state parameterization is done by parameter phi that tells me how well a particular state could be represented. Just to give you an example, let's say I have a grid world. Okay, so I have a 3x3 grid. Just this. And let's say this is an obstacle. So this red block here represents an obstacle. Okay, and just copy paste it. 3, 4 places. Let's say here, here. And imagine the agent is located here. Here. Okay, in this case, agent is here, the goal is here. So the way a state can be represented is dependent on the design of the problem, right? So the way we design the problem is or the way we parameterize the problem. Yeah, the parameterization of a state space is inherently a design problem. Okay. So in this case, let's say when I want to represent it from a global point of view. So in this case, I would say that my agent is located at point 2, comma 2. So when I say 2, comma 2, it means its agent is at row 2 and column 2. Okay. if I want to represent an array, let's say if it's a zero indexed array, so I'll say this is zeroth row, first row, second row. So it's at position 1, comma 1. Or let's say I have an array with index 1. So based on that, it's located at row 2 and column 2. So this is a global representation, right? This is a global representation. That means the agent, uh, the state has the global information of where the agent is at every time step. Okay. Secondly, there can also be some sort of an egocentric representation. That means the agent won't necessarily have the global knowledge, but only based on the surrounding sensory knowledge, it can also take actions accordingly. So let's say I say that the four neighboring walls that I have in the four directions, north, east, south, west, the four walls that I have, if there's an obstacle on the north, I put as one, otherwise zero. So I'll have four representations. So let's say I go in a clockwise fashion, which is north, east, south, west. So I'll write 0, 1, 1, 0. What it reads is no obstacle at north, obstacle at east, obstacle at south, obstacle at west. Okay. So this is kind of an egocentric representation, right? So the representation is based on the agent's perspective or the agent's sensory information that I have. Similarly, another sort of representation is, let's say the agent is at point X and this is a goal. So I need a goal oriented representation. I am trying to look at a goal oriented representation. So I would typically would like to know what is the direction to the goal. So let's say there is some sort of a bearing information that the agent has. So it has an idea of where the goal is, and based on that, it tries to make a particular action. So here in this case, let's say the agent uh, should know that the goal is on the southwest. Okay, since there are eight possible directions, so that also can be represented numerically by 1, 2, 3, 4. Let's say one is left, east, north, west, south, every other direction. So I have represented in letters, but it need not always be symbolic. It can be numerical as well. So that depends on the design problem. Okay, it's inherently a design problem, the representation of state. But the only thing one should keep in mind is that the only condition is that the fees that are represented here should be linearly independent. So that's an important condition. The fee representations here should be linearly independent. As long as it is linearly independent, you are fine. You are fine. Okay, just a second. So there's 20 more minutes left. Let's see what I can cover. Sorry. Yeah. So what I have covered so far. I have covered dental function approximation. So next up comes linear parametrization. So what linear parameterization tells me is that, let's say I have state S1. Okay, represented by fees. So I have P1 of S, I have P2 of S. Let's say S1, S1, dot, dot, dot. I have phi k of S K, S1, right? Similarly, for state S2, I'll have phi1 of S2, phi2 of S2, dot, 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 phi k of S2. Okay. And let's say I have n such states, right? This will be phi1 of Sn, phi2 of Sn, dot, 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 till phi k of Sn, right? So I have n such states. So each when I write phi of s, it component representation for that particular phi as one. So when I write phi of one, when I write phi of one, this gives me the column here. This uh, draw this. So when I say phi of one, it is this particular column over here. Okay, so this is phi one vector. Okay, so this is a vector representation. This would be phi two, and this would be phi k. If I represented it in terms of vectors, right? So what my linear parameterization tells me is that the way I can approximate the value function is so I need to have a good enough estimate of the value function, right? So one way I can approximate my value function v hat of s comma theta is by taking a dot product, okay, of the phi representations and multiplying it with the appropriate parameters theta. So it's just theta transpose phi of s. Okay, I've just multiplied two vectors here. So it's like a dot product of uh, all the individual phis which are weighted by the respective parameters theta. Okay, and once I have that particular v value, all I need to do is I plug it into the theta update equation. So I have what I had. I had theta of t plus 1, theta of t plus 1 was theta of t plus gamma delta t, sorry, should be gamma. Since I have taken the square of this entire term, so it should be, this was a whole square, right? The gradient of the mean squared error. So once I take the gradient of that with respect to theta t, I end up getting, so it's this term. So I'm just evaluating this term by putting instead of v hat, I'm putting this quantity here instead of v hat, right? So it's r t plus 1 plus gamma v hat st plus 1 theta t minus v hat st theta t, the whole multiplied with phi of s, right? Because I am also taking the derivative of v pi of s, which which I'll get as phi of s, right? This is just the chain rule update. Now, more compactly, if I were to represent it for linear parameterization, it should look like this. So this big term inside the bracket I have is nothing but my dt term. Okay, this is the TD error term. I'll just replace that and write it as this times the phi of s. So once I've have this particular representation for a linear parameterization, I can do the theta update in a pointwise fashion, and I can get an appropriate estimation or an appropriate function approximation for the value function v, right? What else? Okay, I'll quickly cover the control with respect to function approximation, or should I say function approximation and eligibility traces. So now we want to look how eligibility traces affects the function approximation that we are taking here. Okay. So in the earlier case, my dt was r t plus 1 plus gamma v of st plus 1 minus v of st, right? So my eligibility traces looks like this. So I have gamma lambda times the eligibility plus here I keep, instead of keeping a track of the eligibility one that I have, so when I do a parameterized representation, I need to keep a track of the gradient of the value function here. Okay, so I have this thing times v of st, right? And once I have that, my theta update term looks like this. My theta t plus 1 is equal to theta of t plus alpha times delta t et, right? Vector. Now notice, I should put a hat here. Hat, right? Notice that the estimation of the value function, I need to take a gradient of that, okay, with respect to the estimation. So if I, this also should be highlighted. It's an important equation. Okay. So now, if my v hat of st, okay, is approximated by some sort of linear parameterization. So let's say my v hat of st comma theta is just theta transpose of phi of phi of s. So if I plug it here, so if I get take the gradient of that, so if I take uh, gradient of theta t, gradient with respect to theta t for v of st theta, I end up with phi of s. Okay, and if I plug it here, I end up getting the same update rule that I had in the previous equation, right? Or in fact, if I were to if I have to represent it as in to what we were doing earlier when we were looking at the value function based method, when we had a lookup table, that means I have that many number of parameters equivalent to the number of states that I have. Okay, that means when I take the derivative of that, I end up getting let me see. Okay, slight disconnection from my end. I have to reshare my screen. Yeah, so this is how eligibility traces would also work when I'm trying to do function approximation, or when I'm trying to do a pointwise theta update over here, right? So this is how this method holds true even for this particular case. Now let's say I want to go for uh, control with function approximation, right? So I want to look at control with respect to function approximation. This is how it should look. So instead of having a phi-s representation for each state, I do an encoding for a state action pair. How? So earlier I had phi of s. So for control, I need to keep a track of, I need to uh, make a state action pair representation. Okay, so this is like, you can think of it as a uh, joint features, right? That we have, that we kind of maintain. And this is true if I have large number of actions. This is true if I have large number of actions, right? Now let's say I have small number of actions. For small number of actions, I so let's say the number of actions that I have is much smaller than the number of states that I can represent. Right? Okay, I think this also got stuck. Let me give me a moment. Okay, let's see. Okay, the update is happening now. So for small number of actions that we have, we need not necessarily encode it into a joint feature because computing a joint feature is a challenging feat in itself, right? So that's why we sort of maintain separate function approximations for each number of states that we have. So let's say in a grid world problem, I can have millions of states, but the actions are to move up, down, left, or right. Okay. So in this case, it makes sense to maintain 4 different function approximations for each different individual actions in such cases. Okay. So in such cases, the actions are don't have any sort of correlations, right? So this is one method to approximate the phi values. Or other way is you maintain uh, the phi of s and just for each individual action you make a linear combination, right? So you just take a dot product. So I have multiple function approximators for different actions. I just make a dot product of that, and that I say is a good enough estimation for my q s comma a. Fine. Uh, and similarly, once I have defined that, so I can directly just define my sarsa lambda for this as follows. So I have E of t plus 1 is equal to gamma lambda E of t plus the gradient of the q function. Okay. So this sort of gives me the control aspect when I'm looking at function approximation. And this q of stat can be directly substituted from here. Okay. And if you put in the algebra, you will get the appropriate eligibility trace update. And once you have that, you just feed it into this particular equation. And let me highlight this also. Once you are uh, substitute in this, you have a method for your policy update, right? Or the policy grid or the policy parameter update part that you have. Okay, so we have 5 more minutes. Should I? Okay, I should just take me 5 minutes to mention state aggregation methods, right? So let's say you have a large number of states. Okay, so let's say this represents a tabular representation of the states. Okay, so each uh, row represents a state, each column represents the next possible state. So the idea here is that you try to estimate that close by states, sorry, close by states have similar value functions. Okay, so in a way, you're trying to reduce the number of states that you have. So the heuristic that you take is that close by states have a similar value function. So that means you're clubbing a state and its neighboring state, and you're saying that this can be represented by one singular value function. So in a way, I club this particular state and say all these states inside this have a same value function. Okay, so this can be done for a continuous action space, for a discrete action space. So let's say this for a discrete space, this can be done in such a fashion. So let's say I have a grid world, big grid world. So close by grids would have similar uh, similar value same value functions in such cases. Okay. Now let's say I want to go to a continuous space, right? So there, this part. So instead of squares, maybe I'll draw circles over here. So this, I'll say this group of states will have the same value function. This will have the same value functions. But now I have to fill up the entire grid also, right? So I'll draw circles around here such that there are certain number of overlaps. And in our case, overlap is good because what it tells me is that if a particular state is overlapped by 2, 3 indicator variables, then that state will be updated twice, which is good in a way because I don't want any sort of jump discontinuity whenever I'm moving from one subgroup to the other subgroup. If there is a certain overlap, then we can say that there is some sort of a gradient that is being formed whenever I'm trying to estimate or update the value function for that particular state. Okay, so this is good for us. Okay, another so this thing is known as coarse coding. This is known as coarse coding. Another popular state aggregation method is known as tile coding. So it works as follows. Let's say I have a grid. So what I do is I start drawing tiles in this grid. So let's say I make a tile which is almost equal to the size of the grid, but shifted by some factor. Okay, so I make a big tile over here. So I'll say this is tile one. Next up, I define another tile. Let's say this is color dot blue. This is also shifted by some particular value uh, over here, and then I draw another tile. Fine. Third up, one more. Sorry, one more tile representation. So the idea is more number of tiles means better overlap and more number of updates that I can make to a particular state over here, right? So this kind of method or this kind of state aggregation method is known as tile coding. Okay. So one big advantage when I'm trying to do coarse coding is that I can get some sort of a gradient in such kind of methods, right? So let's say I have a world in which the agent is here and it has to go to the goal, right? So by means of coarse coding, if I aggregate it, so I know I have some value function which looks like this. Okay. So in a way, my value function is tilting my agent to move towards the goal. So this is how the value function is pushing me towards the goal for a continuous environment, right? But the moment I introduce some sort of a discontinuity, the moment I introduce some sort of a discontinuity, this value function method would no longer work in a similar way because if the value function for this particular state is very high, even though I mean the value function here tends to push me towards the goal, even though there is a wall in between, right? So the way to you know uh, remove that particular problem is to define some sort of a state embedding so that I kind of transform my space. So let's say this is the x-axis, this is the y-axis, this is the x, this is the y, right? So I transform the space such that all this is taken into account, right? So you can think of it like I split open this thing into two separate rooms. So this is from the Cartesian state space, I transform it to some other uh, space representation wherein this region was split into two different rooms. Now, if I define the goal here and start the agent here, it makes sense to define a value function in such manner. So such kind of embeddings helps in avoiding such kind of issues that we have. Okay, this is the x-axis and this is the y-axis. This is a transform y-axis. I should say x prime, y prime, something like that. Okay, so yeah, it's already 8:02. I think I have covered most of the things. I need to cover LSTD and LSPIs. Maybe I'll do that in the beginning of the next class. And thank you for coming. And uh, we have 4 more lectures to go. Let's hope you guys are still enthusiastic about this course in the later weeks as well. All right. Thank you. Have a great day. I'll stop the recording and I'll see you next week. Thank you. Bye.